So far, we have discussed what happens to the ket describing a quantum state of a system when we rotate the coordinate system which we are using. Let me remind you once again, this is a passive transformation. The system itself is not changing. What is changing is the coordinate system. And as a result, the numbers which we use to describe a system will change or may change because of the change in coordinate system. This is different from an active transformation where we actually think of rotating the physical system and keeping the coordinate system intact. We have been consistently using passive rotation throughout. So that is one thing that to be borne in mind. Now, I also need to stress that the fact that the numbers describing a physical state changes when you rotate your coordinate system can happen in quantum mechanics basically through either changing the kets describing the system while leaving the operator the same, or by keeping the kets unchanged, just changing the operators appropriately. We have seen both approaches and both of them give you exactly the same result. Of course, you could also have a mixed approach where both kets and operators change, but that's more complicated and people usually don't use such a thing. Now, let me remind you that we learned that when there is a single system or single quantum system, I will talk about the kets changing in what follows rather than the operators changing. But you should realize that there's a completely equivalent way of describing the same situation with operators changing. Now, if you rotate the coordinate system, then the ket describing a quantum system will change, and we have already figured out that an operator, a rotation operator, u n hat theta, will act on the ket for a rotation of coordinates r n hat theta through an angle theta about the axis n hat. And we have also seen that if the rotation angle is infinitesimal, then this u n hat theta essentially becomes almost the identity with an added first order correction proportional to the angle epsilon, I epsilon by h cross, times an operator which is nothing but the component of angular momentum in that direction. So armed with this knowledge, let us ask ourselves what will happen if you rotate your coordinate system and your quantum system happens to be a composite system, a system made out of two subsystems. So basically, we know how the kets for the systems A and B both change under a rotation of coordinates. The question that we are asking is, the composite system, the system composed of A and B, how do the states of that composite system, which remember belong to the Hilbert space H1 direct product H2, where H1 and H2 are the Hilbert spaces for A and B respectively. So the question we are asking is, how do the elements of this direct product Hilbert space change? And the answer to that is very easy to give for the special subset of states known as the direct product states. Remember, if the composite system is in a direct product state psi1 O times psi2, it means essentially that the system A is in state psi1 and system B is in state psi2. In this case, it's very easy to understand what will happen when you rotate your coordinate system, because psi1 will change by the standard rule for A, psi2 will change again by a standard rule, the one for B. Of course, there's a catch here. The catch is not all states of the direct product system or the composite system are direct product states. In fact, a vast majority aren't. However, once we know what happens to direct product states, we can figure out what happens to an arbitrary state simply by using linearity. So there's no loss of generality if we stick to only direct product states for the time being. So we are asking this question. We are carrying out a rotation Rn hat theta of the coordinate system. What happens to a state psi1 direct product psi2? Of course, you might have noticed that I am using color coding here. The ket and subsequently the operators for the first system will be in red, and operators for the second system and the case for the second system in blue. So here we have un hat theta, the rotation operator for the full composite system, which is in black, acting on the direct product state. We know what will happen, of course. We already know what un hat theta for the system A is. That's the assumption. We know how the states of systems A and B respond to rotations. So un1 theta acting on psi 1 direct producted with un2 theta acting on psi 2. So essentially we are saying that if the system is in a direct product state, then each system behaves essentially as if it has the respective state and responds to external things like coordinate transformations in exactly the same way. Now, of special interest is the case when the angle of rotation is infinitesimal, say epsilon, and we know that for an infinitesimal rotation, if we keep terms up to order epsilon, the operator un hat theta here must be the identity operator, which stands for the case when there is no rotation, plus a first order correction term, which is I by h cross times the angle epsilon, times the operator, which is nothing but the component of the angular momentum operator in the direction of the axis of rotation. So this is what is really acting on the direct product state. So this is the left hand side of the equation. What about the right hand side? The right hand side is straightforward. It's essentially the same kind of thing. You have un1 epsilon, which is identity for the first system I1 plus I by h cross epsilon times the component of the angular momentum for the first system in the n hat direction, this operator acting on psi 1 and a similar operator acting on psi 2. So assuming that we know everything about the systems A and B, which means we know their angular momentum operators, it is very easy to figure out from here what the angular momentum operator J1 cross 2 for the composite system is going to be. So let us see that in some detail next. So this was the equation that we had, and notice that we can expand this out in a pretty straightforward manner. This identity acting on psi 1 cross psi 2 of course gives you psi 1 cross psi 2 back, plus this acting on psi 1 cross psi 2, that's what you have on the left. That's pretty straightforward. On the right, what we have is basically identity acting on psi 1 O times identity acting on psi 2, that's psi 1 cross psi 2 again, plus a first order term coming from this operator acting on psi 1 direct producted with I2 acting on psi 2 and I1 acting on psi 1 direct producted with this operator acting on psi 2. Of course, these are the first order terms. A term like this operator acting on psi 1 O times this operator acting on psi 2 is a second order term, and we have to ignore it. Remember, we cannot take that into account, not only because we are looking only at first order terms, but because there are other second order terms in the expansion which we haven't written down. So just writing down that second order term would have been an error. But up to first order, what you have is simply this: psi 1 cross psi 2 coming from I1 psi 1 I2 psi 2, this term coming from the angular momentum operator acting on psi 1 O times I2 acting on psi 2, which is of course psi 2 itself, and this term comes from the other first order correction, which is I1 psi 1 itself times this thing acting on psi 2. Now we can actually cancel out a lot of terms. Of course, psi 1 cross psi 2 is there on both sides, that can be cancelled out. And after you cancel this out, all terms have I epsilon by h cross, we can cancel that out too. And after we cancel out everything, we end up with this result. And what we have done is emphasize the fact that this psi 2 sitting on this side of the direct product sign is actually identity operator acting on psi 2. The reason for doing that is we now realize that n.j1, which acts only on the Hilbert space for system A, can be promoted to an operator which acts on the composite system just by taking nj1 direct product with identity. Similarly, you have identity 1 direct product with nj2. So this is what you end up with. So since the operators n hat dot j for the composite system agrees with the sum of these two operators on all direct product states, which means it agrees on the entire basis for the composite system, these two operators must be one and the same. So we finally end up with an expression for the angular momentum operators for the composite system is j1 cross i2 plus i1 direct product with j2. So this is the final result for a composite bipartite system. Just to remind you, the word bipartite is simply a fancy way of saying a system which has two parts. We have a total angular momentum operator, which is essentially j1 acting on the first particle state's direct product with identity acting on the second, so nothing happens to the second in this piece, plus nothing happens to the state of the first system, direct product with j2 acting on the second. Now this is often shortened. Now this direct product form of j1 cross 2 is actually the correct mathematical way of writing it. However, this is quite a big thing to write and it becomes pretty cumbersome to keep on writing it all the time. So what we will do is we will write simply j1 cross 2 is j1 plus j2, or simply even j equals j1 plus j2. From the context, it should be obvious that we cannot really add j1, an operator which acts on the Hilbert space of system A, to j2, which is an operator which acts on the Hilbert space of system B. So these are operators acting on different states and simply cannot be added together. So when we say j1 cross plus j2, what we really do is promote both of them to operators acting on the composite system by doing j1 direct product i2 for the first one and I1 direct product j2 for the second one, and now we add them together. So this is really what we do always, but when we write it, we often write things like j1 plus j2. So from the context, it should be obvious whether we really mean direct ordinary sum of two operators, or do we really mean this kind of indirect direct product sums, if you get what I mean. So the angular momentum operators now for this composite system are j square, jx, jy, jz. Jx, jy, jz are the generators of rotation for the composite system. Remember, jx really is j1x cross identity 2 plus identity 1 cross j1, j2x, and so on. And j square is built out of jx, jy, jz in exactly the same way. Okay, now the reason we bring in j square also is something which we have already seen in ordinary angular momentum theory. J square commutes with each one of jx, jy, jz, so it is possible to find simultaneous eigenstates of j square and any one of these operators. By the way, how did we know that j square commutes with jx, jy, jz? Actually, we did not really have to look very far for it. You could have figured out that the commutation relations between jx, jy, and jz are essentially the same relations as between j1x, j1y, j1z, or j2x, j2y, j2z, simply by directly calculating the commutators. But frankly, we did not really have to do that. Remember, we showed earlier that the commutation relation between angular momenta is a direct consequence of the fact that they generate rotations, and rotations of coordinates do not commute if they are about different axes. This purely geometrical fact that rotations don't commute leads to the angular momentum commutation relations. So since our composite system has angular momentum operators jx, jy, jz, the commutation relations between these operators is determined the moment they are angular momentum operators or rotation generators. We don't really have to show that they are the commutators are whatever we usually have for, say, subsystems. Of course, in addition to j square, jx, jy, jz, there are other angular momentum operators. There's j1 square, j1x, j1y, j1z, obviously. There's also j2 square, j2x, j2y, j2z.